Good? Okay. Right, hello. So, my name is Byran. I work for a company called Bluefruit Software. We're based in Cornwall in England. And we provide an embedded software development service. So we don't write our own products. We write software for other people's products. We introduced Agile practices in 2009. And since then, we've delivered approximately 30 projects of varying sizes. Some of them have been very small, only lasting a month. And some of them have been quite long, things up to 3 years. So today, I'm not going to focus too much on the TDD cycle. There's been plenty of good talks on that already. I'm going to talk about the extra bits that I'd like to have known after I've been to one of those talks. So how to apply this to my domain. And my domain is the embedded domain. So although I said I'm not going to mention it, I am going to start with it. So hopefully everyone's familiar with the TDD cycle. So you start off, write a failing test, see it fail, make a small change to make the test pass, see it pass, and then refactor to improve your code and your tests. So probably less well known is the first mnemonic. So this defines a set of criteria that the test should have. So fast, they should be quick to run. Slow tests create a barrier to developers running them, and they'll run them less often. Isolated, so tests must isolate the cause of the failure. The developer shouldn't have to reverse engineer why the test has failed. It should be obvious from the name of the test and the assertion message. Tests should also be independent of each other, and they should be runnable in any order. So repeatable, tests should give you the same results every time. So there are lots of reasons tests can fail intermittently. It can be things like depending on external factors. So your hardware may not return the same value every time, and this can cause your test to fail. It's not a fault of the unit under code, system under test. It's just because your hardware has returned something different. So this means you can't depend on hardware in your tests. There shouldn't also be any non-deterministic behavior in your tests. So this can come from incorrect use of things like threads or processes. So the test should be self-verifying. They should be able to decide whether they pass or fail by themselves. There shouldn't be any need for human intervention to decide if they pass or fail. And lastly, they should be timely. So this means the tests are written at the right time. So if you're doing TDD, it means you want to write your tests before the code. If you're doing another testing practice, at least make sure you write them close to when you write the code. So to show how we achieve the first criteria, I'm going to talk about where we run our tests to keep them fast, how the TDD style we use affects the verification of our tests. I'm going to show some examples of how we insert test doubles and how this keeps our tests isolated and repeatable. And then finally, I'm going to look at some other practices we do within our testing process. So when we started TDD, we first needed to decide where we're going to run the tests. And we started off with what seemed like the obvious option, which was running the tests on the target. And this actually worked relatively well for the first couple of projects. And it worked well for the first few months of our third project. But as our code base began to grow during our third project, this started slowing us down. So we did some analysis of what was slowing the developers down, and we had a repeated step that was taking a long time. So we found deploying and running the tests took a long time and didn't really add any value. We cared about the output of these steps, which was the test results, but the problem was the amount of time it took to get them. And as with anything that slows developers down, they try and optimize the process. So in our case, this optimization was writing larger tests. Larger tests have a knock-on effect. They require larger code changes to pass, and this increases the chance of introducing bugs into the code. So testing on target has the major advantage that you get accurate test results. And it will work if you have a very small code base or a very fast deploy. And that was actually the case in our first two projects. For us, there was 3 main disadvantages. I'm not actually expecting anyone to read all of this. That's there if you want to go and look at the slides later. Most of the disadvantages were because we were relying on the target. So the slower feedback item I've already talked about. Embedded systems tend to have a limited amount of code space and RAM. So the tests are going to be as big as your code, if not bigger. And when you deploy, you need to deploy your code, your tests, and your unit test framework. So unless you have a really small code base, you're going to have to split that up and deploy it in smaller chunks. And this then even elongates the deployment process again. You're going to need a set of target hardware for every developer. So this could be in the form of a development kit, and we do quite often do that. But for us, hardware is often limited availability. It's quite often expensive, and sometimes I've managed to break it. So we no longer exclusively run tests on the target. When testing on the target started causing us problems, we moved our testing process onto our development platforms. So this removed the problem of the tests deploying and running slowly, and we thought everything was great. We had the fast feedback we wanted. We no longer had code and RAM space issues, and we'd reduced the need for target hardware. Our code had ended up more portable. It had to run on both the development PC and the target system, so we'd actually already ported it to something else. And we were also able to use other language features which our target compiler didn't support. So this actually ended up allowing us to be a lot more expressive in our tests. So there were, however, a couple of problems. We were testing code on one platform and then running it on a completely different platform. So occasionally we had code passing all the tests, but it didn't actually work on the target. So usually this was caused by some sort of packing problem due to the nature of what we were developing at the time. And the bugs became harder to discover because we were running the code less frequently on the target device. The changes between the runs were much larger. So we no longer had the small increments that we wanted on the target. And another possible problem is that you are able to write code that may not compile for your target. So we didn't tend to run into this because we were developing in C at the time, but with C++ 11 out now and C++ 14 out soon, if it's not already out, it's much easier to sneak in a language feature that your embedded compiler won't support. So in the end, we settled on dual targeting our tests. I actually think this is pretty common nowadays. In order to do this, we use a modified TDD cycle, which looks like this. So we start off as per normal. We write a failing test. We make a small change, and then we refactor. When all the tests pass, I then compile on my target compiler. So this checks that I haven't used any language features which aren't supported by my target compiler. At this point, if I have run my tests on the target in the last 15 minutes, I restart the cycle. Otherwise, I'll deploy the tests to my target and run them there. This ensures that I haven't introduced something that works on my development platform and doesn't work on my target system. And the only deploying every 15 minutes reduces the impact of the slow deploy to the target. So this actually achieves the fast feedback we wanted, and it also has a few other advantages. We still have more portable code. We're now compiling on 2 compilers, so this increases the chances of us catching errors. Quite often our desktop compiler will pick up something different to our embedded compiler. And we're able to run dynamic code analysis. So if we're using dynamic memory allocation, we run the memory leak detection on our development PC. The desktop compiler often provides a much simpler method of doing memory leak detection than our embedded compiler does. And we've also recently started using code sanitizers. So code sanitizers are extra checks which are added by the compiler into your executable. And they look for various types of bugs that can't be picked up by static analysis. So there's sanitizers that check for undefined behavior and problems like using dangling pointers. So I'm not actually going to go into any more detail on them. If you do want to know more about them, you can go online and Google it. There's lots of information, but I would recommend it. They're very useful, and they. Which compiler I'm using? So actually, when I do the sanitizers, I use Clang. I think it is built into GCC now, but I tend to use the Clang ones. So there are a few disadvantages to dual targeting. So you're still going to need the target hardware. So we do have ways to get around that, which I'll chat about later. You can now only use language features which are supported by both compilers. So this may have actually narrowed the set of features you can use. And you're going to need to maintain 2 builds. You can minimize this if you just use the same build system and switch out the compiler and the linker. So how you split your solution is going to determine how easy your code will be to maintain and test. So nowadays we use a simple layered approach. We develop it over time in vertical slices, and we generally have something which is akin to these layers. And we find the further we go down the layers, the slower our testing becomes. So the closer we get to hardware, the slower it becomes. We have a very thin processor layer which we don't unit test. So this layer only sets processor registers. We found that testing it tends to be a little bit ineffective. Our tests end up closely resembling our actual code. And we try and keep the cyclomatic complexity of this layer to 2 or less. We keep our coupling low. So the more coupling between classes, the harder it is to test the code. And lastly, we stick to solid principles. So I find single responsibility and dependency inversion the two most useful principles. Even if you don't know about any of the others, I think these two are going to vastly improve your code. I'm not going to go into them anymore. I think there's already been another talk on that, and there are lots of articles and books that you can read about, including the Robert Martin one, which I mentioned at the bottom. So, at some point, the unit you're testing is going to end up having a dependency that talks to hardware. So in this example, if I'm testing my BMA 150 accelerometer, and I set up the dependencies in the same way as in the production code, then I'm relying on the Raspberry Pi I2C. So in order to keep my test repeatable, I need to remove the dependency on the Raspberry Pi I2C. So I need to decide 2 things. Firstly, what I'm going to replace the dependency with, and then how I'm actually going to replace the dependency. So I'm going to replace the dependency with something called a test double. So test doubles are objects created to fulfill a dependency for the purpose of testing. Now I'm going to use the same terminology that Martin Fowler uses in his article Mocks Aren't Stubs. I actually believe he took it from somewhere else as well. So there are 4 types of test double which we use. So the first one is a stub. These provide fixed responses to method calls and can also record parameters passed into methods. Dummies. So dummies are used when we want to fulfill a dependency, but it's not going to be used within the test. Fakes. So fakes provide a completely working version of a dependency, but in a faked manner, so something like an in-memory EEPROM. And the last type of test double we use is a mock. So these are pre-programmed with expected behaviors, and the expected behaviors are defined by a set of expected method calls, and then they verify that they happen at the end. So which type of test double we use depends on our TDD style. So for classical TDD, we use stubs, dummies, and fakes, and for mockist TDD, we use mocks. So we found it's worthwhile deciding what style we're going to use, and this is actually something we found out quite late in our TDD adoption. So to illustrate the difference, I'm going to use the example from Martin Fowler's exercise, but rewritten for C++. So I have a task that I want to fulfill an order object from a removable inventory that is implemented by a warehouse object. And I have an example scenario which I'm going to implement, which is given our warehouse has 50 apples in stock and an order for 20 apples. When the order is fulfilled, then the warehouse will have 30 apples in stock. So classical TDD uses what's known as state verification. So there are 2 kinds of objects used in the test. The first kind is the system under test. So in this case, it's an instance of the order class called target. The second kind of object is a collaborator. So these are dependencies of the system under test. So in this case, an object that implements the removable inventory interface is required to fulfill the order, and I'm using a removable inventory stub object as the collaborator to fulfill that dependency. And whether the test has passed or failed is verified using the state of either the system under test or one of its collaborators. So this is the important bit with classical TDD, so it's done on the state. So in this case, it's verifying using the collaborator. So classical testers tend to only care about the final state, not how the state was achieved. If it's practical, then you can use a real object as a collaborator. So the system under test is the same. This time I'm using an actual warehouse object as the collaborator and setting it up with an initial inventory. And lastly, I verify the final state of the warehouse collaborator is what I expected. So testing using real objects has the advantage that you don't need to create lots of test doubles to run your tests. This means that classical testers tend to have a slightly broader definition of what a unit is. There are, however, some downsides to testing in this manner. So code changes that break the logic of the system tend to fail a larger number of tests. So this isn't a problem if you're only making small code changes. It will be obvious which change caused the problem. Testing in this way can also lead to a sacrifice of encapsulation for testability, so adding methods in to verify the state. So as an example of this, in my warehouse class, I'm providing a method called howmanyinstock. So this isn't needed for any of the other functionality I've implemented at the moment. It's only there to verify the test. So the other style of TDD that we use is mock-is TDD. So mock-is TDD uses what's known as behavior verification. So the system under test is exactly the same. This time I'm using a mock object that implements the removable inventory interface as the collaborator, and I've implemented it here using Google Mock. So mocks tend to be quite long-winded to write by hand, so using a framework is going to help. The real difference with mock-is style TDD is that you specify the behavior the collaborator expects. So here I'm specifying that there must be a call to has inventory and then a call to remove inventory. So mock-is testers care about how the behavior is implemented and think about it while they're writing the test. Specifying how the behavior works in the test couples the test to the implementation. So this can actually make refactoring harder, as changes are more likely to break your test. So classical TDD has the advantage that it doesn't specify how the code works, it only checks the final state, and this makes refactoring easier. Its disadvantages are that a single incorrect code change can break lots of tests, especially if you're using the real objects as the collaborators instead of test doubles. And there can also be a trade-off between encapsulation and testability. The advantage to mock-is TDD is that an incorrect code change tends to only break the tests that directly relate to the code. So mock-is TDD makes you think about the implementation of your code whilst you're writing the test. Some people see this as an advantage, some people see it as a disadvantage. So the main disadvantage to mock-is TDD is that the tests are coupled to the implementation, and this makes refactoring harder. So nowadays, I tend to switch my testing style depending on which layer I'm testing. So I use mock-is TDD when I'm testing anything that directly relates to hardware. So this is because the behavior of my code is usually specified by how it interacts with the hardware, so it's determined by the data sheet. So if I'm testing an SPI device and I have to set the chip select line low, then do some reads and or writes, and then check the set the chip select line high, I find having this behavior specified directly in my tests makes my tests clearer. And I use classical testing for everything else. So I prefer my tests at the higher levels not being coupled to my code so that I can refactor more easily. So I've looked at what I could replace the dependencies with, but how can I replace them and what effects does this have on my code and my tests? So there are 3 times you can insert test doubles. You can do it at compile time, at link time, and at runtime. And there are various techniques you can use at each point. So I'm going to show examples of these 3 techniques. These are by far the most common techniques we use at Bluefruit. So to illustrate the difference, I'm going to use some code that I wrote for a course I did teaching university graduates Agile software development practices. So we set them a project of developing a monitoring system that would track how a person's arm moved while they were playing various sports. The system used the BMA 150 accelerometer and some other sensors to monitor motion, and the target platform was a Raspberry Pi. So the BMA 150 accelerometer is an I2C device. So the code and tests were set up as follows. The system under test was the BMA150 accelerometer driver, and it has one dependency, which is an I2C port. When I'm testing, I want to use the mock I2C and the tests, and when I'm building the final application, I want to use the Raspberry Pi I2C and the application code. So the first test double insertion technique I'm going to talk about is using C++ interfaces. This is by far the most common technique we use when we're developing in C++, and we use it for inserting test doubles throughout our software. So when using C++ interfaces, the dependency interface is an abstract C++ class whose methods are all pure virtual. So in this example, it declares 3 methods. These allow setting the device address, reading from the device, and writing to the device. The mock I'm going to inject is derived from the I2C interface. It defines the methods needed to implement the interface. And as this is a mock, it needs to provide a set of methods to set the expected behavior. So I'm actually this time implementing it manually. And lastly, it needs to verify that all of the methods that should have been called have been called, and they've been called with the correct parameters. So for this, it has a verify method. And providing that the insertions that I use in the verify don't throw an exception, I like to call the verify method from the destructor of the mock. So this ensures that the mock always verifies when it goes out of scope. So if I forget to call it or I decide not to call it in the test, it doesn't actually matter. So now I have everything I need to write my test. So first, I create an instance of the test double. I then provide it with a set of expected method calls. And next, I create the system under test injecting my test double. So this is actually the point where I'm inserting my test double that I have control over, so I can verify whether my tests pass or fail. I then exercise the system under test. And finally, as the method returns some values, I assert that they're correct. So in this case, the mock will automatically verify when it goes out of scope that all the expected method calls have happened. So now I have my test, I can write my code to make it pass. So the BMA150 accelerometer depends on the I2C interface, so I need to supply it with an object which implements that interface. So here, I've used a simple dependency injection in the constructor of the class. So this is the code which actually inserts my test double into my system under test. And when doing this, I need to be careful about object lifetimes. I don't want to destroy my I2C before I destroy my accelerometer. So the BMA150 accelerometer object can now use the I2C object that was injected into it when reading the acceleration. The BMA150 accelerometer is not coupled to a specific implementation of the I2C, so I'm free to provide it with whatever implementation I want. So using C++ interfaces is by far the easiest method we use for test double insertion. There are, however, a couple of disadvantages, although they tend to be minor. So the virtual function calls are going to be slower than calling the method directly, and this can be a problem if the system under test has very tight timing requirements. And the vtable will also take up some space, either in RAM or ROM. So the next test double insertion technique I'm going to talk about is using C vtables. So this is effectively faking the C++ interface in C. And we use this technique when we can't use C++, but we still want the runtime substitution. So in this example, I'm actually going to create a simple single instance of the BMA150 accelerometer driver, which allows me to switch which I2C port it's connected to. If I did want to have multiple instances of the BMA150 accelerometer, then I need some more code to allow for the multiple instances. So to implement the C vtables, we use a struct of function pointers. So here I've created a struct called I2C that contains the 3 function pointers I need. For the mock, I need to define the methods that match the function pointer declarations in the vtable struct. So I've only shown the definition for the setAddress function here. The others didn't fit on the slide. I then need to create an instance of the vtable struct, filling the function pointers with the addresses of my functions. Next, I need the methods that allow me to set the expected behavior. And finally, the verify method to check that all the expected method calls have happened. So this time I'm going to have to call the verify method directly in the test. C doesn't provide me with a way of tying my function call to the scope of my test. So again, now I'm at the point where I can implement the test, and the test follows a very similar pattern to the C++ interface. So the expected behavior is specified. The system under test is initialized by injecting the collaborator. So this is actually where I'm inserting the test double, so I can check the test, and then the system under test is exercised. The verify method is called to ensure that all of the calls to the mock have happened, and the return result is checked. So now I have my tests, I can write my code. The code needs to have the dependency injected into it. So the BMA150 accelerometer initialize function will store the injected dependency in a file level variable. This is the code which actually allows me to insert the test double. The BMA150 accelerometer read acceleration function can then use the injected dependency. So this allows me to test the code and have runtime substitution in C. So using C vtables allows us to have runtime substitution in C. It is, however, quite easy to make mistakes in the vtables, especially if you start adding in methods at a later date. It's quite easy to forget them. And if you want to have multiple instances, there is a lot more boilerplate code that goes with it. So the final technique I'm going to talk about is inserting test doubles by linking other object files. So we use this technique when the system on a test is time critical, so usually down at the driver level, and the virtual function calls have become too expensive. So the example I'm going to show is in C, but this works exactly the same in C++. So with this technique, dependency injection is just the function declarations of the I2C. We don't want any virtual function calls, so the system under test is going to call its dependency directly. The trick with this technique is that I switch the code implementing the dependency at link time. So when I want to test the code, I link the mock I2C and the tests. And when I want to build the application, I link the Raspberry Pi I2C and the application code. The important part is that these two files contain different definitions of the same methods. So this can actually be relatively easily achieved in a make file. When I want to build the tests, I link the mock I2C and the tests object file. So this is actually where I'm doing the insertion of my test double. And when I want to build the application, I link the Raspberry Pi I2C object file and the application object file. In both cases, I'm linking the same object file for the BMA150 accelerometer. So I'm testing as close as possible the code that will end up in the final application. So the mock needs to implement the dependency interface. The trick here is that the method definitions must match the method declarations from the dependency interface header. Next are the methods which allow me to set the expected behavior. And as with the other techniques, I need a verify method to check that everything that was expected has happened. And again, the test follows a very similar pattern to the previous two techniques. So the expected behavior is specified. The system under test is exercised. The real difference is that here there's no need to inject the dependency. That was done at link time. The verify method is called to check that all the calls to the mock have occurred. And lastly, the returned result is checked. So as the dependency has been injected during the linking stage, there's actually no need to inject it into the code. The system on a test is able to call the dependencies directly, and this means that I have no virtual function calls. So inserting test doubles by linking other object files remove the need for virtual function calls in time-critical units of code. It does, however, add complexity to the build system. So in summary, we use C++ interfaces for everything when we're coding in C++. We use C vtables when we can't use C++, but we still want runtime substitution. And we link other object files when virtual function calls become too expensive in time-critical areas of code. So, what else? So when hardware is in short supply, we actually use our continuous integration server to run tests on the target platform. So this means we only need an instance of the target hardware on our CI server. So this is possible because of the way we set up our source control management. So we use Git, and then every developer has a fork of their code, of the code. Our continuous integration server will then monitor all of the forks, and when a developer pushes a branch to their fork, the build server will download it, build it, deploy it to the target, and then run it on the target platform. Our developers then get either a toaster notification about the result, or they can just look on the information radiator, which is shown here. So we tend to have two types of integration tests. We have integration tests that check the hardware interaction. So the photo shown here is an integration test setup I'm currently building. So these tests check that our code actually talks to the hardware correctly. We also have integration tests that only run in a simulated environment. So these check that the interactions which can't be tested using the hardware actually work. So things like error conditions. It's quite often difficult to get our hardware to actually generate an error when we want it to. And the final practice I'm going to talk about is something we call polymorphic system testing. So this is something we're currently experimenting with. So polymorphic system testing is a technique where we switch the target of our system under tests from running on the code on the actual hardware to a version of the code running in a simulated environment. So we started experimenting with this technique because we had a problem with one of our projects. So the project was a system for removing impurities from water, and because of this, it had processes that took hours to run. This had a knock-on effect that when we ran our system tests, they also needed to take hours to run, even if they're automated. So this slowed down some of our outer feedback loops. So we have many layers of feedback loops to stop us introducing bugs into our code. So the first feedback loop we have is the other person in our pair, and this usually gives us feedback within 5 seconds. Our unit tests run at least once every 5 minutes. There's kind of a rule in unit testing that if it takes longer than 5 minutes to implement, you're probably doing something wrong, and it's probably you're making too big a test. We ran our integration tests approximately every half an hour, mostly because they took a little while to run. From when we submit our code for a code review until we start getting feedback from it, usually takes us about half a day. Our system tests for the new code we'd introduced usually took a couple of days to run, and this wasn't ideal. But the slowest feedback was provided by our regression tests, which took approximately a week to run, and this was still even if they're automated. So our regression tests didn't usually find bugs in the low-level drivers. These were found by our integration and our unit tests. They found bugs in the application layer when we changed a sub-process that was used in many larger processes, and that the change we'd implemented wasn't meant to be in all of the larger processes, it was just meant to be in some of them. So in order to speed up this feedback loop, we wanted to modify our automated system testing. So our automated system testing was implemented using SpecFlow in C#. So up at the top, we have our gherkin scenarios. So these specify how the system should behave. They're written in English so that we can easily discuss them with our clients. Below this, we have our step handlers. So these match the English text and convert them into method calls on our step routing. So in this example, we're testing that the EDI stack turns on when the water is flowing past it. The given step requests that the simulated water stops flowing, and the step handler forwards that to the step routing. So the step routing receives requests from the step handlers and routes them to the appropriate hardware on our system test support framework. So this will either fake an input or read an output. So in this example, the flow rate is routed to a PWM on the system test support framework. And the system test support framework is the same thing we use for our hardware integration testing. So it's quite nice because it ends up, we get lots of code we use from that. So for our polymorphic system test, we wanted to keep the test scenarios and the step handlers the same. These define what our system should do. The section we wanted to switch was the code that routed the messages to the system test framework. So to do this, we took the top level of the step routing and converted it into an interface that we could easily switch. When we wanted to run against the hardware, we created the hardware routing which we already had. And when we wanted to run against the software on the development PC, we create the software routing. So when we're testing using the software routing, we remove the code that interacts directly with the hardware, and we replace it with a fake BSP layer. So this fake BSP layer tends to come from our unit tests. This means that we receive feedback from the tests in a much shorter time. So tests which used to take hours to run against the hardware now only take seconds to run against the software. And this gives us much faster feedback about when we've broken something. And importantly, we only use the software tests to check if we've broken anything. As we're not testing the entire system, we don't use it to say it's definitely working. So, in summary, I've talked about how we keep our tests running fast by dual targeting, how we use different TDD styles and how this affects the verification of our tests, how we use different test double insertion techniques to keep our tests isolated and repeatable, and some of the other practices we use in our testing process. So thanks for listening. And are there any questions? I was actually expecting questions during. Yep.
Okay, one question on the remark. The remark is regarding switching the implementation between the tests and actual hardware. You are showing the trick with changing the binary during linking. You can actually do very similar thing by replacing headers. So actually you have a very similar header that does some operations like, I don't know, set something into register, change pin state or stuff like that.
Yep.
And then because you have it in header, you can inbuild with single line just split between implementation for hardware and for testing. And then you do not need to actually do a function call at runtime on your target platform, unless, of course, you have a compiler that does a really good job with link time optimizations, right?
Okay.
So that's like quite a good benefit. And actually, logically, it's the same. It's just like way faster. It's very important when you are doing like bit banking protocols or stuff like that.
Yes. So yeah. So when we're doing bit banning stuff, then we do actually switch out of the linker. But yes, you can do it with includers as well. Hello.
Hi. It's somewhat more of a comment really than a question, because when it comes to mocks,
Yep.
what you're doing is verifying that the controller or whatever it is talking to the thing, is doing the right thing. Correctness is based upon what it does, because there's no state to test. For instance, in a web controller, there's no state. In an algorithm, there's no state. It's all in the things underneath. So actually, you need to do that one. Also, what I didn't notice you talking about is sequence, such as you often in tests, I mean, you've got the Google log tests there, you want to say, I have to do the reset before I do that one. So if you do, for instance, you weren't testing that you set the address before you read, it would be quite possible to have those the wrong way around. Your tests pass, but the hardware, but then the software doesn't.
Yeah, so that actually, we do actually do that, and we do actually have our tests assert that it happens in the mocks.
Have any sequencing in
The earlier ones did.
Okay.
Yeah, so we do that, yes, and I do acknowledge that. It may be that I didn't make that clear, sorry.
So what leads to the ones I came in a little bit late when I saw some that didn't have any verification of ordering them.
Okay.
Okay. Some of the later ones haven't got ordering in them, but which is actually critical?
So actually the way we do it is, because that was a custom mock which we're writing by hand, it's the order they're added in the test.
Okay.
So because the order of setting the behaviour is set the address, then do the read or the write, that is the order they get checked in.
Okay, so there's an implicit ordering in the way. Okay.
Yeah. Hello.
One more thing, on one of the slides you showed that you're using if-defs to change the implementation for doing this high-level software testing. And again, here you could actually do this trick with replacing objects or headers at the build time, and it will be like way better because you already have it in place, right? Like the infrastructure, and cutting code with if-defs is usually a source of a problem.
Yes. Yeah, so you can do it that way. The other way we do it sometimes is we have tags on our tests. So with SpecFlow, we can actually just tag them, and then certain ones run against hardware, certain ones run against software. And it's quite a quick way of just switching without having to rebuild everything. Yes?
I was wondering if you've played around with the GCC trick of using the wrap and reel.
The wrap and...
Linker wrapping.
Yeah, linker wrapping. So the benefit is that then you can choose in your test whether you want to mock out, because right now you completely remove the I2C, the Raspberry Pi I2C.
Yes.
So that was of course okay there because it's so low level.
Yeah.
But sometimes you want to mock out a part of your subsystem.
Mm-hmm.
And then by using this linker thing, you can choose whether you want to mock it out and redirect it to a mock or a stub or something. Or you can actually just set a flag and then you can go to the real code.
Okay.
Yeah.
No, we've not...
It's a little hidden gem in GCC.
Yeah, so one of the problems we have quite often is that we don't get to choose the target compiler, so we can't always use things like GCC.
So this is for my off-target.
Oh, if you're off target, okay.
Yeah.
You can also use the instrument function part. GCC also has instrument function. You can instrument your functions. There's another interface for doing similar thing as well as the linker wrapper. You can actually do it in the compiler, but not the linker. You can do it in two places. So instrument function says, well, it essentially allows you to intercept a call to a function. And the compiler will do that, rather than the one they all talk about, the wrapping function, which is actually done by the linker. There is an equivalent on the Microsoft one with the p-enter stuff. I don't know if you've seen any of that.
No, I've not.
SpecFlow and things, it probably makes me think you're using Windows on your development.
Yes, so on our
There are
development...
actually some techniques you can use on the Windows compiler there with a thing called p-enter, which
Okay.
is part of the profiling one, which will basically call your function. It calls the function p-enter before it calls the main function. Part of the profiling stuff, so you can actually use that for substitution.
Oh, okay.
So it's a way of doing sort of kind of transparent mocking.
Okay, I'll have to take a look into that. Thanks for that. Ooh. Any other questions? James?
You mentioned you're using leak detection, and I also saw you using Google Test. So did you add leak detection to Google Test?
Yes, so we have a test listener, which just monitors the amount of memory that's allocated at the start of the test, and then checks that it's still the same at the end. So yes, we do that, and then that happens for every test.
Simple counter or something more complex?
So because we're doing it on Windows, Windows has a facility where we can monitor how much has been allocated. So we just use that.
Or you could override operator new and do the same thing without the listener.
Yes, so that is another option as well.
That's what CPPU test does.
Right.
Overrides new and delete malware complete.
You could also use a listener for seeing how long the test took to run,
Yep.
because that can be a critical thing. If suddenly you put in a degradation, something now takes 10 milliseconds to take, something which can be for timing related things can be very useful.
Yes. Yeah. Anything else? Cool. Okay, we'll call it there then. Thank you.